quick show of hands for people who are in the room. So who here is a .NET developer? Quick show of hands. All right. Now, no worries if you're not a .NET developer. A lot of the concepts I'm going to introduce here will be useful even in other programming languages and runtimes. The actor model, which is what essentially the design the Akka.NET implements, is available in a lot of different programming languages. Second question, who's heard of the actor model before? Quick show of hands. Actually, more than I expected. All right. Well, no worries if you've never heard of that either. I'm going to get into it. So a little bit about me. So my name is Stannard. I'm one of the founders of the Akka.NET project. My work with Akka and Akka.NET started back in, 2013. I just quit Microsoft and started a venture-backed marketing automation analytics company. I was full of piss and vinegar at the time, as the expression goes. And we needed to build, we had a successful a successful analytics product that we had built, and we were working on launching a second product all around marketing automation. And one of the key requirements that our business had was that we were processing campaigns for lots of developers on the Windows Store. So we had thousands of apps, tens of millions of concurrent users, all hitting our servers at any given time. We needed the ability to very quickly make a decision about which user should receive which push notification from the developer of the app. It was like in-app marketing automation. And in order to achieve those extremely low latencies, we needed a paradigm that was different than how traditional software designs looked. Our marketing automation system fundamentally looked like this little diagram off to the right, where you have a bunch of stateless web servers talking to a database, and then a bunch of back office applications that sit behind it and talk to the same database. We didn't use SQL, we used Apache Cassandra, which was great for doing analytics. But this is largely how most web applications have looked over the past, we'll call it 3 to 4 decades. Well, these are relatively inexpensive to build, and they're straightforward for developers to follow. Most of the complicated aspects of building a web application are outsourced to the database in this design, worrying about things like durability, data consistency, transactionality, etc. And that's why these designs are increasingly popular. But the trick to making these designs work is centralization. In order to have that inexpensive experience, you have to outsource everything to the database. And that probably works well for, I would wager, 99% of applications. It worked well for our application, even though it was extremely high traffic, needed the ability to scale up and down, and we had to have relatively low latency requirements for our analytics piece as well. But these designs lend themselves to a couple of inescapable problems. Being a single point of failure is probably the most obvious. Single point of bottleneck, a little bit less obvious, but probably more painful in the long run. Because even when your system's not failing, you're still going to struggle as a result of all traffic converging in one area. And then finally, centralized designs are impossible to scale horizontally. Reason why that is because basically all you can do is really scale vertically. You can go ahead and try to run that single centralized source of truth on larger machines, but you're ultimately going to run into eventually problems of that design. Good example, I have a customer that is running on the largest possible SQL Server instance right now. I think it's 1024 cores. I can't imagine what the licensing fees are for that, but I imagine it's more than the salaries of most of the people in this room times 10, probably. They literally can't get a bigger instance than that, and they're still having problems due to lock contention, meaning that adding more cores might actually be making the problem worse to a degree. So when you run into the following conditions, high demand, high availability, or real-time processing constraints, these are going to be the environments where your centralized design is going to start to show some strain. Now, our analytics application had high demand and had high failover and fault tolerance requirements, and we didn't need Akka.NET yet for that application. Reason why was the database we chose was actually fairly distributed, decentralized, and scalable. But when it came down to this real-time processing constraint that our marketing automation app needed, there was no escape. There is no way to make that work with a database. And the reason why is it's impossible to reason about concurrency if the same user's state is being processed by 4 different web servers, which is what would happen under our traditional design, just like this. So what do we need to do to try to deliver these types of applications, which, by the way, are becoming increasingly common? The key factor here is the real-time processing constraint. A lot of software that was developed 10 years ago didn't really have real-time processing constraints because it wasn't economic. Didn't have fast enough internet bandwidth for a lot of users. Smartphones were kind of a relatively new thing still. They're ubiquitous these days. And web browsers had no support for real-time processing technologies until, I'd say around 2013, 14 or so. That's when WebSockets became ubiquitous. On top of that, IoT has really taken off as a segment. It's now much more feasible to go ahead and build things like industrial IoT. When most people think of IoT, they think of, honestly, kind of stupid stuff like smart locks and smart refrigerators, and that's junk. Where IoT really makes money is in settings like manufacturing, energy production, transportation, and really it's like sort of enterprise IoT is really where the money's made there. Those are all classes of applications that have these real-time processing constraints. So the purpose of my talk today isn't necessarily to say Akka.NET's a drop-in replacement for HTTP microservices. That would be crazy. That's not the purpose of my talk. The purpose of my talk is to introduce you to some concepts and to show you when you're going to need to apply them, not necessarily to go ahead and evangelize a new way of doing everything. Akka.NET is very useful when you have real-time processing constraints, when you have high availability requirements, and when you need the ability to scale horizontally. So what we're really talking about in terms of trying to address those problems that our cheap, centralized, database-centric apps have is decentralization. In a decentralized application model, the source of truth is pushed to the endpoints of the network rather than centralized in a database. And what do I mean by push to the endpoints? It means your application is the source of truth, not the database sitting underneath it. So what this gives us is basically a peer-to-peer network, in essence. A peer-to-peer network that exists in a server-side environment. When most people think of peer-to-peer programming, we think of things like BitTorrent and file sharing. Multiplayer video games often implement peer-to-peer networks on the client side, using stuff like UDP multicast usually. This is about server-side peer-to-peer programming, where everything is under your control. It's your company owns the network end-to-end. So these decentralized networks have a couple of big advantages over centralized ones. The first is that it's very easy to add new edges to the network, adding new nodes and new edges. This means that you can scale linearly. If I double the number of processes that are running my code, I am going to literally double my total max throughput and my bandwidth. And that's because by adding more points, I create more locations where work and state can be performed and stored. Next is that decentralized applications are extremely fault tolerant. All peers are created equal in a peer-to-peer network. One peer crashing or being kicked out of the network during an auto-scale operation, or let's say having a type of software error like a deadlock, isn't going to render the rest of the network inoperable. We're simply going to stop routing traffic to the affected node and route it everywhere else. So peer-to-peer networks are fundamentally self-healing in ways centralized ones are not. The other key facet of this is that multiple nodes are all capable of performing the same work, meaning that in a peer-to-peer network, you can have what's called a heterogeneous network, which is just like a microservices environment where there's different processes that do different things that all interoperate together. But you want to have multiple redundant copies of each, just like you would in a centralized application as well. And lastly, here's the trade-off. The reason why peer-to-peer networks aren't so common in server-side environments is they're not cheap and inexpensive in the same way that centralized solutions are. So like I mentioned earlier, those centralized database-driven applications are probably the right call most of the time. But the applications where you have these low latency and high availability requirements also tend to be probably the big money makers at your company. These aren't stupid back office applications that get run once a month. These tend to handle mission critical workloads, they tend to be customer facing, and they tend to carry a lot of, let's say, the business's income. So how do applications become decentralized? Well, the most important thing about decentralization is that all of these applications have state, meaning when you send them data, they remember it and keep going. It's not like fire and forget systems like our normal, let's say, sort of database-driven programming, where we trust the database to carry all that for us. There's actually units of work inside each of these processes that have the ability to accumulate state and react to changes in it as it happens. And this is what actors are going to be used for. The other thing we need in order to build a decentralized application is something you almost never see in a stateless app, which is known as topology awareness. Topology awareness means every single process needs to know the address of every other process running in the network. That way I can route a message to it directly if I need to. Your web servers typically don't, if you have web server A, it has no idea that web servers B through D exist, because it doesn't need to. Everything runs in isolation in that process. In a decentralized application, the work gets distributed across all of the other, let's say, nodes of the same role type, for instance. When I say a node, I really mean a process. So if I start conflating terms there a little bit, that's what I mean. Now, crucially, in a decentralized application, you're not going to see load balancers or other intermediaries like service meshes, because that's centralization. You have the ability for nodes to address each other directly in this network. Now, what your application model looks like, imagine A through F here are all Akka.NET processes that are all being run maybe inside their own Kubernetes pod, maybe they're being run on their own virtual machine, or if you're like a lot of our customers that exist in, let's say, heavily regulated industries like healthcare and finance, you might actually be running multiple of these on bare metal like Windows machines, potentially. Well, these processes accumulate state, and the role the database plays here is the database is where we go and make that state durable so it can be recovered in the event that we do a deployment, or in the event that we redistribute state, or in the event that we have to take the whole system down and bring it back up. The database is essentially a parking space for our data. It's no longer the single point of failure inside the system where everybody needs to read and write everything coming out of it. Typically, your workload in this type of design is going to be, if you're looking at this from the point of view of the database, is going to be much more write-heavy than it is read-heavy. Actors are going to persist their state as it changes, or persist the events that cause their state to change. Event sourcing gets used really heavily with actors. And when those actors crash, or get restarted, or get redistributed in the event of, let's say, scaling up or down, they're going to go to the database to try to recover that state and become reentrant. They're going to try to reenter the previous state they were in. Now, I haven't actually talked about actors at all yet, so let's get to that. What is an actor? The original actor model white paper was written in, just to kind of give you a sense of history here, was written in 1973. That makes the actor model about 2 years younger than the relational database from a conceptual standpoint. It's been around for a long time. Now, next question you're going to have is, well, if it's been around for that long, why have I never heard of it? The answer is computer scientists originally envisioned the actor model as a means of doing multi-core programming back when computer scientists thought computers were going to be the size of a warehouse. And these are going to be, cathode ray tube machines that would, there'd be like 5 of them in the United States or whatever. Moore's law eliminated the need to have that type of hardware architecture in the first place, so the actor model was dormant for a long time. It found new life in the dawn of the internet. The original implementation of the actor model is called Erlang. It's short for Ericsson language. Ericsson implemented Erlang to build the first digital telephony exchanges when they were building modern digital telephony networks that power all of our cell phone communication now. That's what Erlang was originally created for in about the mid to late 1980s. It was open source in the early 90s. And since then, the actor model was kind of used primarily by large internet giants who had to build low latency applications. Good examples of that in the 90s were the first ad exchanges where you had the ability to bid on ad impressions. That was one example there. Erlang is still used quite heavily today. WhatsApp runs entirely on it, as do a lot of other telephony services. Quick show of hands, who here has used RabbitMQ at work before? Congratulations, you use Erlang and the actor model. RabbitMQ is implemented on top of it. So given that, let's go ahead and talk a bit about what actors actually are and how we should think about them as software developers. I named the slide here that you can think of actors as cloud objects, where if you work in, let's say, the insurance industry, and you're tasked with creating an application that can go ahead and give users instant quotes online, this is like an important part of your user acquisition process if you're an insurer, you might go ahead and have one actor represent one quote for one user at any given time, right? That actor has internal state. And when I say state, it just means C# properties and fields. Nothing fancy, no crazy serialization magic. It's arbitrary properties and fields like any other class. Actors work by processing messages. Every single actor has a little queue that sits in front of it. It's basically a concurrent queue in C#, for lack of a better word. And when you send a message to that actor's queue, the actor will be scheduled to drain all the messages from that queue in the order in which they were originally received. First in, first out order, right? What this means is that since actors can only process one message at a time, all of the updates to that actor's state are going to be automatically thread safe. There's no need for locks, no need for critical regions, or any of the other sort of shared state concurrency mechanisms that you've probably used when working with, let's say, the task and parallelism library or async await. This actor will process updates to its state as it processes those messages, and it has the ability to react in real time to changes to that state. So for instance, if you wanted to build a multiplayer game and this actor represented an NPC, and let's say you're casting a spell on it or attacking it or whatever, each of these events might represent something that's going to cause the actor's state to change. Maybe it's going to lower its health, maybe it's going to give it a debuff or whatever. And what's going to end up happening, let's say you end up damaging this NPC enough to kill it, it's going to send a push notification to the client, letting the client know you have killed me and I am no longer in your game state, right? That's an example of sort of how actors can be modeled. Now, I kind of messed up my PowerPoint sequencing when I was editing this last night, so apologies there. But users typically map actors one-to-one to business entities. And what makes actors so useful is all actors are guaranteed to have at least one globally unique address, meaning that all of these cloud objects can be addressable from anywhere inside our application. So if I have 1,000, let's say, processes all running in my big Akka.NET cluster, any one of those processes can talk to one actor on any of the others. So it makes our state addressable this way. Next, actors accumulate state in memory. They react to changes in real time to that state, so they don't run on like a batch process scheduler. When you send a message to an actor, that actor is going to register itself on the .NET thread pool and is going to try to process a burst of up to 30 messages at a time, however many accumulated in its mailbox. And all of this can be done without any external infrastructure. Actors don't require a database, they don't require access to some sort of centralized web service, and they don't really depend on things like a specific cloud provider or anything like that. Actors can run in any arbitrary environment. Now, we typically use some of these tools, like I use Akka.persistence, which allows me to persist my actor state to a database of my choice, but it's not a requirement for me to get this type of system up and running. It's something I can opt into if I want to use it. And the way processes typically look, let's say from the point of view of one process in our network, we have a process tree, a hierarchy of actors like this, where I might have this root actor. This is built into Akka.NET, the user actor. And then I have top-level actors that represent different parts of my domain. So if I'm building a multiplayer game, I might have my NPCs actor. I might have another top-level actor that represents chat. And then maybe I have another actor that represents the actual players that are in my zone right now, where I'm keeping track of their position, their stats, their health, what's in their inventory. And then let's say under my NPCs root actor, I might have, let's say, groups of different types of NPCs. So enemies, I might have friendly non-player characters, any other, you can kind of use your imagination here to see where this might go. But this sort of process hierarchy is sort of how we organize domains within a actor-based application. Now I'm going to get into more detail on this in a moment, but I want to take a step back and get back to our business use cases. Now that I've had a chance to introduce the actor model, talk about what it is and how it works, let's talk about why you'd want to use it. What are some business use cases where actors get used pretty frequently? So in terms of some of the customers I've worked with over the past 8 or 9 years, sports betting is a really common thing that Akka.NET gets used inside of, in particular for doing things like real-time odds calculation, where if you think about it, the odds on a football game or a horse race are basically the price, in other words. So we have to do real-time pricing. Monitoring systems, we have everything from customers that use Akka.NET to monitor the health of patients while they're connected to, let's say, an anesthesia dispenser in a hospital, all the way up to doing things like monitoring the volume and temperature and pressure of oil pipelines. Lots of use cases there. IoT gets used quite heavily. Marketing automation is sort of my background. Akka.NET gets used quite heavily there. And even more sort of interesting stuff like enterprise integration, where you might have a warehouse that's connected to a fulfillment partner, And you use actors to manage sagas for being able to group shipments and get them loaded onto trucks. There's lots of different use cases. And some examples of customers who use Akka.net. I'll just go ahead and step through this real quick. These are some of our customers. So we work with Bank of America, ING, big shipping companies like BNSF. United uses us for being able to do, they're actually not a customer of ours, they just use the open source, but they use us for actually doing real-time price search on united.com. That's what it's useful for. Lots of different use cases here, and these are all examples of, like I said, business-critical applications. You don't use Akka.net typically in, let's say, your back-office payroll application. That's probably not where you'd want to use it. But for doing things like keeping track of where your fleet of vehicles are at any given time, or being able to allow customers to search through all your inventory in order to make a purchase, or being able to go ahead and process analytic events coming from a large array of medical devices and sensors. Akka.net's a great fit for all these things. And the reason why it's a great fit for these things is the one common trait they all have in common is low latency. So that's the one point I want to keep drilling into everyone's head, is that Akka.net gives you the ability to deliver low latency applications that are highly available and can scale. Now, the trick to that low latency is what I showed you earlier, is the state, the fact that actors have the ability to accumulate state in memory. The key to low latency is using a principle known as state locality. It means that the information you need to do your job is adjacent in memory to the code that does it. That way you're not serializing requests, round-tripping to a database. That database might even have to perform disk I/O. It's going to have to serialize everything back into a response, transmit it over the wire. It's going to get deserialized again. That's one of the tricks that we need in order to go ahead and actually deliver low latency applications. We've got to cut that process out. So in this case, we're just using adjacent registers in memory on the machine that owns that entity. The other thing we need in order to deliver low latency is a way of reasoning about concurrency. We need to make sure that all requests for the same business entity all go to the same place. The actor model's addressing system and the fact that actors work by processing one message at a time gives us the ability to do that. So, how do we make decentralization easy? Well, the actor model, not this actor model, but Akka.net is the way to do it. Now, what is an actor exactly? I've answered this a little bit already, but it's an object that has a globally unique address, and we can only interact with that object by sending it messages. That's the only way to do it. You can't invoke a method on an actor remotely. The actor model is not designed to do that, and it will, by design, make it very difficult for you to do that. That's sort of the old world RPC model that does not play nicely with high fault tolerance and high availability. Now, all messages are meant to be immutable in order for the system to work. That's more important when you have messages being broadcast to multiple actors in the same process than it is when you're going over the network. And the reason why is because of serialization. But generally speaking, you want your messages to be record types. That's kind of the best practice for working with actors. In F#, all of your types are immutable by default, so you don't really have to think about this. But in C#, you want to go ahead and use record types, and you want to make sure you're using things like the with keyword to go and make immutable copies of that when you modify a message. Now, all actors can be thought of as a self-contained microprocess. My state is private. No one else has the ability to modify my state other than me. And the only way I modify my state is when I'm processing a message someone else sent. This gives me a huge range of control. Good example. If I have a complex workflow that I need to implement through my actor, a good example might be, we've got a lot of customers in the travel industry. If I need to go ahead and book a vacation package, which involves flights, hotels, rental cars, possibly excursions, there might be a whole saga workflow I have to get through in order to successfully deliver that. Actors can do things like inspect the message that's coming in and say, okay, this is a message coming back from the rental car provider. I'm going to mark that stage of my workflow as complete. This is a message coming in from, let's say, a flight provider, and oh no, they've told me that the flight I just thought I booked, that seat's no longer available, and I'm going to have to essentially dump core and restart because I can't fulfill this customer's request. Or alternatively, I can see a message and know that I'm not ready to process it yet. This message is, basically pertains to a later stage in the process. I'm going to buffer it, and I will go ahead and store that inside what we call a stash in Akka.net. It's just a little interface you use to decorate your actor. And I will unstash that message once I've received all the other ones that I get. This allows us to build things like state machines, which are basically how you want to reason about complicated processes. If you want to model a workflow, state machine is probably the easiest way to do it. And that's all self-contained internal implementation detail inside one actor. And the best part is, because actors are inexpensive resources, they take up about 1 kilobit of memory by default. And if they don't have any messages, they don't use any CPU. So actors are fairly inexpensive resources. I can have millions of workflow actors all running in parallel, but only a small number of them might be processing messages at any given time. So I don't have to reason about basically what everyone else is doing. I just designed one actor to handle one instance of one workflow that I can spin up as many of them as I need in order to fulfill every user's request. Now this is what an actor type actually looks like. We've talked a lot about some of the concepts so far. Let's look at some code. This is a base type in Akka.NET known as a receive actor. And what distinguishes a receive actor from other types are these strongly typed receive statements right here. So actors can have internal state. In this case, my only state is a logger. Not super exciting, but like I mentioned earlier, actor state is just properties and fields. There's nothing special about them. The state doesn't have to implement some built-in Akka.NET interface. There's no constraints on what your state looks like. It's whatever you need it to be. These are the real workhorses of Akka.NET though, your receive statements. This receive statement is basically a declaration that every time this actor receives a ping message in its mailbox, it's going to run this function. So I'm going to run this function every time I get one of those. And I can only process one message at a time. So if I had another typed receive or another type of message here, I don't have to worry about both of those running concurrently. Actors can only process one message at a time. They're serial processors. That's what makes all the actor state thread safe. So this actor will go ahead and come up with a reply time. And this property down here, the sender, is a reference to the actor who sent us this message. So I can automatically reply back to that actor with one message, or I could send them a stream of messages potentially, where I send them maybe every single time I receive a new event that relates to this workflow, I might push a notification to that actor. Now in this case, I'm using the scheduler to do a delayed reply back to this actor, but I can just do sender.tell and instantly reply back to them if I want to. And the way we create actors is through what's known as an actor system, which basically creates the address space within one process. So typically there's one actor system per process. I'm going to show you an example of a real production app where we tie into the Microsoft.extensions.hosting library, and we just go ahead and use the service collection to instantiate it. But the actor system is basically what allows actors to communicate both in memory and over the network. And then we go ahead and use props to declare, here's my actor type, and here's some constructor arguments it might need. And then I pass that prop class into my actor system's actor_of method. I can optionally give it a name. If I don't give it a name, a random one will get assigned to it. And then I get this actor reference back. That iActorRef is a transparent handle I can use to send that actor a message. Now, that actor might be implemented using a class. So let me take a step back for a second here. This actor will receive this ping message asynchronously. This means that that message will be queued into the actor's mailbox, but not necessarily processed right away. The actor is in control over how it processes messages and when it processes messages. When that tell message exits, it's just a guarantee that that has been queued into the actor's mailbox, or if I'm going over the network, that tell method will exit when I've queued that actor for transmission over our networking system, which uses TCP basically internally. Now here's a really important trait about actor references and why they're so useful for building distributed systems. Is they implement a really important property known as location transparency. Quick show of hands, who's heard that term before, location transparency? All right, we got a couple of brave souls here. Location transparency is something we use every day as consumers. This is totally blanking on the actor's name, but the character's name is Gordon Gekko from the 1980s movie Wall Street, using one of those 9-pound cell phones they had back in the era there. Cell phones are a great example of location transparency. Michael Douglas, there we go, finally remembered it. Cell phones are a great example of location transparency. Now who can tell me what part of the cellular, let's say sort of apparatus, is it that gives us location transparency? The cell towers are the network that delivers the messages, but it's really the cell phone number. The cell phone number is a logical address for a physical resource somewhere out in the world. The cell phone tower is able to figure out how to translate that cell phone number into that physical location. So my mother lives in Houston, Texas. I'm here in Atlantic Beach. If I go ahead and call her cell phone number, the cellular network is going to figure out how to translate her logical address into her physical address and route my voice packets to her. Likewise, if I fly back to Houston tomorrow and I call her again, the network will be able to repeat that feat over and over again. So what location transparency allows us to do is communicate with objects without needing to know where they are. DNS is another good example of a system that provides us with location transparency, right? The actor reference is location transparent, meaning if I call iactorref.tel like I did here, that actor could be running. Now, I know because of the way I just created this actor is for certain running in the same process as me right now. But if I get that sender iactorref that I had in my couple slides ago, that actor could be pointing, that actor reference could point to an actor running in my process. It could be pointing to an actor running in a remote process. You, as the Akka.NET developer, do not need to care or distinguish which is which. Akka.NET will automatically take care of the routing and serialization for you to make sure your messages get to wherever they need to go. That's a really crucial trait for building decentralized systems because, well, this is basically, by the way, what an Akka.NET address actually looks like in practice. You have sort of your protocol scheme, name of your actor system, the address that your node is running on, and then you have basically the location of where your actor is in the actor hierarchy, which basically kind of follows a logical structure of parent, child, all the way down. Now, why actors for distributed systems? Stateful programming is crucial for being able to build low latency applications. There are certain types of applications you can build that are low latency that don't require actors. A good example of that would be something like a content management system, but those are somewhat limited in terms of what capabilities they can deliver. If you need to build, let's say, a real-time logistics system, you're not going to get very far using just a database and stateless web applications. That thing will fall apart pretty quickly. The location transparency we just talked about makes decentralization possible. Specifically, what it facilitates is the ability to bring new processes into the network and communicate with them without needing to know their address. Let's compare this to something like using an HTTP client. If I needed to go ahead and specify the address of which server I'm going to talk to with the HTTP client, where I have to explicitly address everything, that would be quite cumbersome after a while. What the iactorref allows us to do is communicate with an actor without needing to know its implementation type, without needing to know its location. All I need to know is if I send it this input, I should expect this output in return. The messaging contracts essentially are the only things we really need to worry about over the network. We don't need to worry about implementation types or addressability. That's all taken care of for us by Akka.NET. Now, one of the things that's also useful about location transparency, I'm working with a customer right now that builds software as a service. And one of the requirements that drove them towards Akka.NET is that in order for them to land some large enterprise customers, they have to enable real-time collaboration between multiple employees within the same company, all using their service on like one document at the same time. Their application is relatively low latency right now, all powered by WebSockets, all running on .NET, but it's mostly CRUD. It's kind of built around a storage system they implemented and SQL Server. Well, one of the things they need to do in order to enable collaboration is they have to have actors control the flow of all these different people trying to make edits to the same document. Someone has to be the traffic cop to organize all of that. If it's a free-for-all and all these different web servers are all trying to write to the same object without synchronizing with each other, it's going to be very difficult to go ahead and maintain a consistent view of that document. In other words, SQL Server's innate locking tools don't help you at all when you're trying to reason about the concurrency of the application. So they need a model to be able to go ahead and reason about that in a highly available, low latency, decentralized fashion. But they absolutely do not want to develop and test their application while they're building it that way. That would be ridiculously slow. Akka.NET through its location transparency, makes it very easy to test and run all that functionality inside a single process where everything happens in memory. The fact that we're distributing it later only really shows up in terms of, let's say, dealing with latency possibly, or dealing with possibly network failures. As long as you go and price that into the way actors message each other, i.e. use timeouts and things like that, it's very easy to go ahead and test and run all this locally in one process. So even though you're building a big, scary distributed system, your development experience can still happen on a very tight loop where you get lots of feedback from your test system and from the compiler while you're working. And then once all that's implemented and you follow this sort of actor-based design, it's actually pretty trivial to scale this horizontally. Just for kicks, I was doing some work for a large sports betting company in Europe, and they needed me to measure certain different Okta.NET configuration options to try to understand why they were having big spikes in CPU consumption. Turned out to actually be a bug in the SQL client is what was causing it. But I went ahead and built a little sample app using Pulumi and Okta.NET, and I scaled it from basically 0 processes to 400 basically nodes all running in one Kubernetes cluster in the span of about 30 minutes. And the 30 minutes was how long it took Kubernetes to start stuff up, not how long it took Okta.NET to do things. Now, let's talk a little bit about, in practice, how would I actually use actors to do anything? What's the real methodology here? In practice, what actors are really good at doing is taking big problems and reducing them into small, manageable ones. Good example. Imagine we're building an IoT system. I have thousands of devices, and there might be many different types of devices all on my network, and I need to try to make sense of it. So if I'm building a transportation network, or if I'm running an automated factory, or if I'm running, let's say, an oil pipeline, or if I'm an energy company and I want to keep track of data from power meters that are connected to 40 million homes, I need some way of reasoning about that fire hose of data. And let's say if I use that energy provider case, I need to turn that data from each of those power meters into invoices. Or I need to turn it into operational data to show where draw is happening on the power grid so I can balance it. These are actual examples of Okta.NET applications in the wild that are out there. Well, in order to make that possible from a software development perspective, we have to take that giant fire hose of data and break it down to small parts that one software developer can successfully reason about. This is where actors really shine. We take this fire hose of events and we can inspect, okay, what type of device did this message come from? Was it a temperature sensor, a volumetric sensor, a pressure sensor? Was it a gauge? Where did it come from exactly? And I can say, okay, based on the type of device, I'm going to route those messages to device A entities here. So I have a parent actor that owns all devices of that type, all volumetric sensors. Then I might look, okay, what is the sensor ID? So which sensor, which volume sensor sent me this packet? Might belong to device ID 1. So I route those messages to that actor. And that actor owns all the state for that sensor. And let's say that volume sensor has a surge that lasts for longer than 30 seconds and goes beyond some critical safety threshold. At that point, that actor is going to react and probably notify a human maintenance team that there's a problem. And it might also go one step further and actually tell the valve upstream from it to shut off. Oh, actually, it's probably going to be another actor that would do that. It would probably receive that event and say, okay, if we've got a safety issue, we need to go ahead and basically cut thrust in the pipeline here until someone looks at it and clears the alarm. Pretty common for a lot of industrial IoT systems to have like real-time sort of safety rules like that. While on the other side over here, I can have another group of actors that are looking at temperature data. The temperature sensor on the same meter of pipeline as the volume sensor, due to the ideal gas law, will probably also detect a problem at the same time. So when you see both the temperature, pressure, and volume sensors all converging, I think the projector just shut off. Well, this would be a good opportunity for me to talk about fault tolerance with actors. The methodology for how actors deal with failures, in fact, let me move over to the, yeah, here we go. I actually got that slide up and running. So how do actors deal with failure? Well, unlike this projector, which is a single point of failure for my presentation, the way actors deal with it is like this. Let's say, going back to our IoT example, one of my actors processing messages for a volumetric sensor throws an exception. And that exception could be for any number of reasons. Maybe we got a malformed message. Maybe we're p-invoking into like native driver code for this actor, God forbid. Or maybe the programmer who wrote this, trying not to insult anybody, maybe this was a JavaScript programmer working with .NET for the first time. You never know. This actor throws an invalid operation exception. Because we have a process tree, parents supervise their children. And I see that unhandled exception get thrown by that actor, and I go, well, gee, what am I going to do about this? By default, the way the actor model works, and this is actually a fairly robust default like error handling pattern, is we reboot the actor, is what we do. We tell the actor, you know what? Apologies for the native exception thrown by your driver. The only way for us to probably fix that is to have you reboot and restart. And what will happen in that case is your previous actor instance will destroy itself and get garbage collected. And you know that props formula we saw earlier? We're going to use that to recreate that same actor with exactly the same constructor arguments that it had before. And if you're using something like Okta.persistence, where we have the ability to replay messages from the database, that actor will try to recover its state from the database and then resume processing messages once again. When an actor restarts, none of the messages that are sitting in its mailbox are lost, and its actor reference is still valid. We're basically doing an in-place reboot of this one little isolated piece of code. So the other thing that makes this so powerful is that this actor throwing an exception and being restarted is totally transparent to the rest of the system. There's no contagion effect, in other words, where when this actor throws an error. So actors have a really high degree of fault isolation, and because the way they reason about their work is just processing a queue of messages, the actor can reboot and resume processing as though nothing happened before once it recovers its state. That gives us a pretty powerful fault tolerance paradigm that you don't get in normal procedural programming. And it's because of the fact that actors have the ability to essentially change how they process messages while they're doing it. So the actor might go ahead and recover its state and then resume processing from thereafter. So this fault tolerance model is really crucial for being able to build high availability applications because typically errors are a matter of when, not if. And when they happen, we need to have a strategy for handling them. What most developers try to do is they implement what I call dig out code, where you have a bunch of catch blocks that'll try to restore the code above it to some sort of workable state. And that code is absolute trash. It's impossible to test, rarely works, and it's very difficult to reason about very generic errors like invalid operation exceptions. If I don't know why the error was thrown, I should probably just let the actor crash and restart. SQL connection timeout, I can infer what might have caused that. Probably SQL Server timing out. But an invalid operation exception, I have no idea what caused that. I'm going to reboot and see if it goes away.
So in that case, is the exception message thrown back to the parent through queuing, or?
Basically, so the question was, how does this actually make it back to the parent? There's internal messages that are basically sent automatically by Okta.net. The parent will receive basically an envelope that has the exception the actor threw in it. Also has a reference to the actor that threw it. And you have the ability to write what's called a supervisor strategy. It's a property you can override on the parent actor here. And you'll basically be able to say, what should you do when an actor throws this type of exception? Restart is the default and probably the safest, but you could also do things like permanently kill the actor, or, and this is, the analogies with Okta.net get kind of morbid. We talk about killing children or taking poison pills or killing ourselves, kind of a lot in here. Don't take it too seriously. In this case, one thing we could also do is the parent actor might say, wow, my child actor really screwed up in a horrific and unimaginable way. It is so bad, in fact, that I'm going to treat this as my failure and ask the grandparent what I should do. And you can use this to trigger a rolling restart, basically. We actually use that for doing things like managing our socket connectivity, where if the socket reader actor notices the connection was aborted, it kicks it up to its parent, the socket writer, which kicks it up to its parent, the reliable delivery supervisor, which kicks it up to its parent, the endpoint manager. An endpoint manager might say, all of you suck, and kill all of them at the same time. Question?
So if a grandparent kills off a parent, does it also kill off their children?
Oh yeah.
Okay, so
yeah, there's no orphans in Okta.net. This is all sort of the Jim Jones family tree here. So yeah. So yeah, in order for a parent actor to stop, all of his children must first be dead, is one thing there. On top of that, one little pattern that I wasn't going to get into, but since you asked, one of the things you should do as a best practice in Akka.net is make your children do all the dangerous work. You want it, so it's like, I had to kill a copperhead snake with a shovel the other day. In the Akka.net universe, I would tell my 1-year-old, all right, good luck, honey, and send her out to go do it. And the reason why is the parent typically has other children. If that parent actor restarts, they all die by default. So you typically don't want the parent actor doing anything that could cause that. The side effect of all your children dying is, just like in the real life, undesirable, right? So we try to go ahead and isolate dangerous work to the edges of our actor hierarchy. Now the next bit here is that actors are really good at scaling and distributing. This is an example of a special type of actor called a router. Routers use strategies like round robin, broadcast, or random to distribute messages to, let's say, other actors possibly running on other processes or other actors running in the same process. This is an example of a clustered, I think it doesn't really matter what the routing strategy is, but it's a clustered, let's say, round robin router for argument's sake. So this process knows, so node 1 knows about all the other nodes in the network, and all of the other nodes in the network know about node 1. That router actor has the ability to subscribe to messages that come from a library called Akka.cluster. Akka.cluster will tell it when nodes join the network and when nodes leave. And we'll dynamically update our routing table to match. So when I send a message to my router actor, that message could go to the foo actor on any of those nodes. I, as the sender of that message, don't need to know or care which one got it. As long as I get a reply back, I'm in the clear. Does that make sense to everyone?
How is the state reconciled between the 3 user foos on your diagram?
That is a great question. Let's see if I can get to that. See, what time is it? I've got about 15 minutes. The way state is reconciled, there's 2 modes for distributing state. In fact, you know what? Since we're in casual mode after our little projector failure here, I'm just going to light speed to the front of the presentation. All right. Boy, I really overdid it here in terms of the amount of stuff in here. All right. That's what I thought last night. I was like, yeah, I can do all this in an hour. Distributing state inside an Akka.net cluster. There's 2 strategies for doing it. Is this the right slide? Distributing work. Yeah, it totally is. Okay. There's 2 modes for distributing state. I'm only mentioning the one I recommend that 99.9 trailing for a while % of developers use, which is using a technique called cluster sharding, where those foo actors all own a separate range of entity IDs. So imagine you use, let's say, a 32-bit regular integer for your entity ID. So you have customer 0 through, I think it's 2 billion and change is the max value on there, all those different IDs. If you have 3 nodes in your cluster, each one of those nodes might own 1/3 of that possible range. And based on which node owns what, we know which messages should go where. We use a technique called consistent hashing to guarantee that. That's not something I was going to get into because that's very fun and that's how a lot of other distributed systems like DynamoDB and Cosmos use that internally, for instance. But that's basically how we do it. The tool that I recommend you use for performing that type of entity distribution is Akka.cluster sharding, which guarantees that there will be at most 1 copy of every unique business entity in the system at any given time. And it's able to guarantee that even when weird stuff like network partitions and process crashes occur. So it's a pretty robust way of doing that. The other reason why cluster sharding is a good way to do it is it guarantees an even distribution across all nodes. So we'll go ahead and make sure that if I have 10 million entities and 4 servers, I can go ahead and guarantee that there's 2.5 million running on each. That's what the sharding system will do. Go ahead.
So if you're guaranteeing there's only one of a unique identity or entity, there's no redundancy, then you're guaranteeing if anything goes wrong, there is some latency occur instead of multiple things processing the same thing and whoever first wins responds.
So the question, to rephrase what you mentioned, is that if there's only 1 copy of a given entity actor, well, when I say 1 copy, I mean like for user 0, there's only 1 actor that owns his state. We're basically saying that in the event that that server is unavailable, we're guaranteeing there's going to be some latency until we basically fail that over and another server gets it. And the answer is yes, which is where the alternative model for distributing state kicks in, which is much more advanced, which is a technique called distributed data, where there's multiple writable replicas that synchronize with each other for that actor state. Customers in sports betting will use things like that for synchronizing the odds, because if let's say you went 30 seconds without knowing what the odds were in a popular soccer match, you might lose like millions of dollars. So they'll use distributed data for that. Most businesses do not need that much. They need more consistency than availability in that case, in which case the cluster sharding model is the right tool for the job there. So that's the only reason why I didn't bring it up, is DData is very cool, but it's also one of those things that most businesses probably won't need. For those of you who are distributed systems nerds, DData works by using special data structures called conflict-free replicated data types, CRDTs. You can kind of think of it as dictionary A can have 2 rows inserted into it, dictionary C can have a 3rd row inserted into it, and they'll both merge together and give you a consistent view of what happened in the order in which it did happen. So that's used for things like Google Docs uses it for being able to synchronize edits on a concurrent session, for instance. Now, where was I? Here we go. I think we've talked quite a bit about this. Let's go ahead and actually talk about some more code-centric stuff for the last 10 minutes here. So installing Akka.net. Akka.net, the core Akka package on NuGet, gives you the ability to create actors, create actor systems, send messages, all the core basic stuff is all in that one module. And if you want to go ahead and play around with Akka.net, here's what's really cool about it. Akka.net does not need to be run exclusively in large-scale distributed systems. You know, I wrote an Akka.net application that could download real-time ticker events from Coinbase and try to help me figure out how to trade cryptocurrency back in the last crypto boom we had in 2017. That all ran inside one little process there. I've also written command line tools and other little dinky apps like Azure Functions, all using just local Akka for stuff. But when you want to build big distributed systems, you want to start using tools like Akka.remote to allow multiple actor systems to communicate with each other. That's where all the networking comes into the picture. Akka.persistence to give actors the ability to recover their state from a database. So I use Akka.persistence usually with Azure Table Storage as my backend, just because one fewer SQL database in the world is probably a good thing. Akka streams. Not going to cover it in this talk, but it gives you a link-like syntax for being able to write some fairly sophisticated workflows. We just had a presentation a couple weeks ago from the developers at Echo, the shoe company. They use Akka Streams for managing their real-time machine learning system. So where they're trying to figure out what shoes should we send to what store and what time frame, right? So it's all like using machine learning for supply chain logistics, essentially. So you can find that on Petabridge's YouTube channel. Akka.cluster is the big kahuna for building distributed systems. This takes Akka.remote and adds the ability to gain topology awareness. You get notifications when a new node joins the network or an old node leaves. Also gives you those clustered routers that you saw in the previous slide for being able to distribute messages to multiple endpoints. And then on top of that, we've got some other tools built on top of Akka.cluster for things like sharding, distributed data, and then another fun package, Akka.cluster tools, which gives you things like a decentralized topic broker for being able to allow actors to communicate via publish and subscribe sort of paradigms. Now, this is a slide I wanted to make absolutely sure got into this presentation because this is brand new. In the past, if you've looked at Akka.net, you probably saw Hocon and which is our custom configuration format that developers seem to take issue with it, even though it's basically just strongly typed JSON. And I don't know why untyped JSON is somehow preferable to it, but whatever. If I had to explain all the idiosyncrasies of software development, I think I'd need another like 3 hours to do it. You no longer need Hocon to configure Akka.net anymore. This is us attaching to a minimal ASP.NET application. You just go ahead and install the Akka.hosting package, and you can go ahead and say, all right, I want to turn on remoting with clustering, with SQL Server persistence, and then I can start and declare actors all right here. So essentially all of my Akka.net configuration and my ability to declare actors is all very strongly typed and ties in very nicely to .NET's dependency injection system as well. We've got some YouTube videos that go into more detail on this. Not going to bore you with all of it here. But this is what we need on each instance of an Akka.net process to get the actor system up and running and into a cluster. And what a cluster actually looks like is multiple Akka.net actor systems all working together. Each of these represents typically its own process. It might be running inside a Kubernetes pod, might be running on a VM. We're adding support for things like Azure Container Apps and Azure App Service right now to try to make it easy to run clusters in there. But each one of these little actor systems has its own hierarchy of actors, and the data running in this actor system here is probably going to be different than the data running in the actor system to the right. That's decentralization. If actor system A on the bottom left corner here died, those actors could be moved to actor system B and we could recover its state. That's what tools like Akka cluster sharding do automatically. So this is Akka cluster in a nutshell here. Now, one thing I want to explain a bit about it is Akka cluster is not magic. Actors are always deployed by default into the actor system that declared them. So when I call actor of, I'm getting a reference to a local actor that is inside my own process. So that's, everything's all local. The cluster forms automatically at startup. We try to basically use what's called seed nodes, where you give me addresses of other nodes that are probably going to be in the cluster at some point in the future. And once they are, everyone's able to connect and able to start communicating with each other over some TCP connections. And internode communication, I don't know why I put that there, but internode communication is opt-in, meaning that you're only going to start communicating with actors and other processes when you use tools like Akka cluster sharding or clustered routers. Now, the thing I'll end with today before I take some more questions and give you my sales pitch is that what makes actors great for decentralization is that their location on the network is transparent to you. You don't need to know where they are. You don't even need to know if that node existed when you first deployed the application 2 months ago. Auto-scaling can bring a new location to the network. You can use it while your system is busy. You can pull that location back out when things calm down. And the Akka.NET programming model will support all of that with minimal fuss. So you ultimately don't need to care about where work happens inside your network or about what the implementation type is of the actor doing it. You just need to know if I send it this message, I expect this response or these responses back. And as long as that programming contract is fulfilled, everything's good on both sides of the connection. So I'll go ahead and skip to the end here. Like I said, I probably bit off more than I could chew. Boy. Thank you very much for your time. I'd be happy to take some questions. I'll be around all day today. My handle on Twitter is Aaron on the web, so you can get a hold of me there. But otherwise, thank you very much for your time and attendance. I really appreciate it. And I'd be happy to take any questions you might have. So thank you. Oh.